As always, take a look at your to-do list and make sure that you're reading the assigned chapters and any other articles, and you're really checking that assignment outline, your course schedule, topic outlines, course schedule, so that you're looking at when your assignments are due. Take a look at your learning objectives. All right, so let's get started. So how your variables are defined, whether they're discrete, categorical, or continuous, will help determine the type of statistical test you'll use when analyzing your data. Discrete variables are numeric variables that have a countable number of values between 2 points. They can be represented by whole numbers, say 1, 2, 3. Categorical variables contain a finite number of categories or distinct groups. You can think about categorical variables as categories on Jeopardy! Each category is its own distinct group. But note that categorical variables can be ordinal when they have a natural order. So they have a natural order of things. 1, 2, 3. One comes before 2, 2 before 3, etc. Continuous variables are also called interval variables because they represent numeric values that can really take on any number. 1.23, 2.5, really be any number. They don't have to be whole numbers. When developing your study, you're going to need to determine what each of your variables are. What are they going to represent? For example, is your independent variable categorical or continuous? The same for your dependent variable. Remember that your independent variable causes a change in the dependent variable. There are many resources available that can help you decide what statistical tests to use, and you can click on the link on this page for the UCLA Institute for Digital Research and Education, and this will take you to a table, and you can figure out what type of statistical test to use based on how your variables are described. Now let's talk about levels of measurement. There are a number of ways to think about measurement within variables. Nominal scales are typically used with categories. Here, the relationship between categories is mutually exclusive but consistent. So examples of nominal variables are things like name, gender, blood type. Each category is mutually exclusive, but they're consistent. Names are always names, gender is always gender, blood type is always blood type. Within each of the categories, each answer is consistent, meaning it's related to the overall category, but the answer is mutually exclusive. Peter and Paul are both names, but Peter is exclusive from the name Paul. Note here that yes/no responses can be considered nominal. If you're administering a test with multiple choices, or say a true-false answer, there's always going to be one correct response and the other responses are going to be incorrect. So yes and no are nominal, can be nominal. Yes equals 1, no equals 0. Ordinal scales are ranked categories. This means that the categories will always have a greater than or less than relationship between the values. One thing to note that although we may know that value 1 is greater than 0, we don't always know the distance between 1 and 0. Think back to our discussion of Likert scales. A Likert scale can be used to determine attitudes about a particular question. For example, the question might be on a scale of 1 to 5, with 5 being really like and 1 being don't like, how much do you like chocolate ice cream? We know that 5 is greater than 1, but that's all we know. There's no true value placed on the numbers. Interval scales place a rank order and equal distance between units. A great example of this is a thermometer. Each value on the thermometer is an equal distance, and there is a rank order for each increment. This means that for each increase, or I suppose a decrease on the thermometer, it represents a higher or a lower number than the previous. Ratio scales are interval scales, but there is an absolute 0 point, and 0 represents the absence of the property being measured. Ratio scales allow us to measure actual amounts. For example, we can say that one person equals twice as much as the other. Ratio scales allow us to truly measure what that amount is. Let's take a look at this in a table format, and this table is actually adapted from your book. So it's table 4.1 in your book. The table represents the measuring of step length for 4 subjects. And we're going to break it down: nominal, ordinal, interval, and ratio measured. So if we were measuring someone's the step length in a nominal fashion, the data would be recorded as categorical. It was a long step or a short step. We could place a person in the category based on what their step length was. But we really have no idea how to translate this to a quantifiable number. We just know one step was long, one step was short. We don't know how long a long step is or how short a short step is. If we were measuring by ordinal data, we would use a categorical method as well, but it would be ranked. A 1 might indicate the smallest, and the 4 might be the longest step. But we really don't have a sense what 4 means, so not a true quantitative measure, but we know that the length that we assign to 4 is greater than the length we assign to 1. If we were again to measure the step in an interval method, it again would be recorded categorically, and we would know the distance between 4 and 5. We would know it's an equal distance. So equal distance 4 is to 5, and an equal distance between 5 and to 6. But once again, the numbers are arbitrary. So unless we know what they represent, we really can't determine what a 5 means. We know that there are equal distance between all of the increments, but what does that 5 mean? I'm really not sure. And then finally, the last way to measure, the ratio measure. Here, the information is recorded and the exact length, based on the exact length of the step. Because this measure has a true 0, so 0 represents no step, we can measure the exact distance between each interval and therefore have a true sense of the distance taken for subject A through D. For example, if we look at the table in the column marked ratio measure, we could say that 23 represents 23 inches, an actual measurement. So let's talk about descriptive statistics. So descriptive statistics describe a quality or summarize the information about a category. For example, we might want to know how many subjects selected a particular category, and descriptive statistics can help us with that. Information from descriptive statistics can be represented as a frequency distribution, which is what you see on the screen. Here we have 48 subjects, and the score represents the scores of 48 therapists on a test of attitudes towards working with geriatric clients. From this table, we want to determine the frequency that each score or level happened, and we want to know the overall percent of the responses and the cumulative percent. So typically we have a statistical program to do this calculation, but this is a small representation, so it's sort of easy to do or to eye. So we would count up the number of times each score appears. So how many times does a score of 9 appear, or 10, or 12 appear? This becomes your frequency. We want to then take a look at our percent. So a quick calculation of each number divided by the total number of samples gives us our percent. And finally, we want to look at the cumulative percent. This is just that. It's accumulation or an addition of each of the percent. So we start with the first, then we add the next percent, and so forth. And voila, that is how you create or calculate a frequency distribution. So what do we do with this information? Well, one thing we can do is we can produce a histogram. By showing frequency, we're providing order to the data and helping to identify patterns within the information. The frequency from the table we just reviewed is plotted in this histogram. So on the table, we said that the score of 9 had one response. The histogram provides a visual depiction of that information. Quickly, we can see that the score of 15 had the highest amount of responses. And so you could pick any number and see, what level of responses that were received. On a histogram, the frequency is plotted on the y-axis, and the variable being measured is typically plotted on the x-axis. So frequency is the y, and attitude score is the x-axis. Frequency data can also be graphed to show how the data is distributed. Figure A is representative of an equal distribution, meaning each measure is the same, just a little square. Figure B depicts a normal distribution showing a symmetrical distribution. Figure C represents a skewed distribution. In this case, it's skewed to a positive or a right skew. And figure D represents a left skew or a negative distribution. While frequencies are helpful to identify patterns, measures of central tendency help to identify the center of the distribution. There are three measures of central tendency: mode, median, and mean. Mode represents the number that occurs most frequently. And if we think back to the frequency distribution that we saw, 15 had the highest number of responses, so 15 is the number that's most frequent. Median is a rank order of numbers. So you would range all the numbers that were found in rank order, and then you would find the center point within the group so that there are an equal number of numbers to the left and an equal number of numbers to the right. So for example, if you physically arrange the numbers 1 through 10, the center point would fall between the numbers of 5 and 6. So the median would be 5.5. You would average the numbers 6 and 5. So add them together, then divide by 2. And so the true median between 1 and 10 is 5.5. The mean is the average of the numbers. So mean is simply the average. When using interval or ratio scales, mode, median, and mean can be used. When using nominal scales, only the mode is really helpful. Remember, nominal scales measure categorical data, so only the frequency of the response or the mode is useful there. These figures represent the mean, median, and mode when representing symmetrically distributed data. So that's on the top. A would represent symmetrically distributed data. The figure B is representing data that is skewed left or negative skew, and C represents data that is skewed right. So you can see how the mode, median, and mean fall in the skewed data. So note that in the left, or what we refer to as the negative skew, the mean is to the left of the median and mode, while in the right, or the positive skew, the mean is to the right of the median and mode. This is due to the fact that the mean, the average, is greatly affected by the overall sum of the numbers. If the data has a number of outliers, then it will pull the average in that direction. Measures of variability represent the dispersion of the data. Range is simply the difference between the highest and the lowest values. For example, if you have scores where the lowest value is 5 and the highest value is 10, then the range is between 5 and 10. Percentiles are used to describe a score's position within a distribution. Percentiles divide data into 100 equal portions. A score is located in one of the portions. If the score is within the 95th percentile on an exam, this means that you scored better than 95% of other test takers. Percentiles allow researchers to compare scores to others within a group rather than just to evaluate just the score. Quartiles divide a distribution into 4 parts, or 4 quarters. Quartile 1, or what we would refer to as Q1, represents the 25th percentile, Q2, the 50th percentile, Q3, the 75th percentile. Since Q2 represents the 50th percentile, it also is the median. Let's take a look at a box plot, which is a visual depiction of quartiles. Each box here represents the interquartile range Q1 through Q3. The end of the lines represent the range. So these little long lines with like a horizontal bar across the top represent the range, the minimum and maximum values. Q1 really represents the range from the minimum value to the Q1 line. The line in the box that's depicted by Q2 is the median, and then Q3 represents the range from the median to the end top of the box, so where I've marked Q3. Q4 is not shown, but here it would represent the range from Q3 to the maximum line, so that long thin line with that little bar on top, so the top end of the range. So when reading a box plot, think about what all of those different quartiles mean. A normal distribution shows a smooth bell-shaped curve. The area to the left of the center matches the area to the right of the center. They're sort of mirror images of each other. Or they're mirror images of each other. The center of the curve represents the mean, and as scores increase or decrease, the slope of the curve moves left and right, so negative and positive. Statistically, several other terms are important to think about when you're looking at curves. The first term is standard deviation. Standard deviation tells us how far the score is from the mean. In general, we say 99.7% of the data fall within 3 standard deviations of the mean. 95% falls within 2 standard deviations of the mean, and 68% falls within 1 standard deviation of the mean. And this is a good depiction of what I've just said. So you can see the different percentages and where they fall as far as standard deviation. If the standard deviation were smaller, it would mean that the scores were more tightly clustered around the mean and the distribution would be taller at the mean. If the curve is wider, it's more spread out, it's flatter, it means the standard deviation is larger and farther from the mean. This is another picture of a standard deviation. Here you can see that the theoretical percentages for each tail, positive and negative, when the data is more spread out. So it's got a lower curve, a flatter curve than what we saw on the preceding slide. Calculating standard deviation is very important, and I know I've included information earlier about how to do this calculation. The steps to calculating standard deviation are on the screen so you can see those. I've also included a video link so you can click on the video camera, or you can just go to this week's session folder, and I've included a link to the video on how to calculate standard deviation. So please take some time and just to go through that and see how it's calculated. Welcome back. So research often uses standardized scores to report data. For example, you might see something like BMI Z-score. This is a standardized score. If we know the standardized mean for a given measure, then we can calculate a standardized score. So here's an example of the formula. Z here represents the standardized score. The X represents an individual score. X with the line over it, what we would call X bar, represents the mean of the scores, and S equals standard deviation. So you can actually compute a standardized score based on this information, or if you have this information. So let's do it. So take a minute and do the calculation for the Z-score, and then graph the score and think about what it means. So what is the Z-score? Graph the Z-score, and what does this mean? So if you plug the information into the formula that was on 2 slides ago and you did the calculation with that data, the correct answer is -1. But more importantly, what does -1 Z-score mean? The minus tells us that it is negative or below the mean, so the score sits below the mean. The 1 tells us it is 1 standard deviation from the mean score. So let's take a look at what this looks like on a graph, and often this makes more sense visually. This is a representation of the information graphed. The score was 58, and this represents a -1 standard deviation. A standardized or Z-score is only used when there is a standardized reference point. So here, our mean was 68, the score was 58, and that represents a -1 standard deviation. All right, so up until this point, we have been talking about descriptive statistics. Statistics that talk about the categories of data, but often this isn't enough to actually test a hypothesis or theory. To do this, we need to look to statistical inference, and inference allows us to estimate characteristics about a population from sample data. Descriptive data just simply describes it, but we need to think about statistical inference if we want to know what this data really means. To discuss statistical inference, we really need to talk about probability. Probability is used as a means of prediction that something will happen. In terms of research, probability is used to predict the chance with random samples that are thought to reflect the population under study. The definition of probability is the likelihood that any one event will occur given all the possible outcomes. When signifying probability, we use lowercase p. Probability results are expressed as a ratio or a decimal. For example, if we were to flip a coin 1 time, there are 2 possible outcomes. 1 equals head and 2 equals tails. We will get one of 2 possible outcomes. We can express this as 0.5 or 1/2 and say that the probability of getting heads is 50% or p equals 0.50. What if we wanted to determine the roll of dice and we wanted to know what the chance of getting a 6 was? The possible outcomes are 6. Dice has 6 sides, or we'll say it's a 6-sided dice. The sides with 6 is one of the possible options, so we would say the probability is 1/6 or 0.167. We could also say the reverse. The probability of not getting a 6 is 5/6 or 0.833. Probability is used in research as a guideline for making decisions about how well sampled data estimate the characteristics of the population. For example, if we know that the average adolescent eats 0.65 cups of vegetables a day, with a standard deviation of 0.25 cups, we could say that 68.26% of the population eats between 0.40 and 0.90 cups. Let's take a look at this on a graph because that often makes more sense. Probability is used as a guideline for making decisions about how well sample data estimates the characteristics of the population. So here is the data I just mentioned in the previous screen. The mean or the average that adolescents eat is 0.65 cups of vegetables a day with a standard deviation of 0.25 cups. So um, at one standard deviation, the amount someone would eat is 0.40, and at a plus one standard deviation, the amount someone would eat is 0.90. How did I get that number? 0.65 plus 0.25 or minus 0.25. Where did I get the 68.26%? Well, based on the normal distribution, remember, at one standard deviation below or above would sit 34.13% of the population. We add those together and we get 68.26%. If we look at the information plotted on a graph, if our sample is 100, we would say that there is a 68% chance or 68 out of 100 chance that any one adolescent will fall within the range of eating 0.40 and 0.90 cups of vegetables each day. But remember, probability tells us what should happen, not what does happen. When using smaller samples of a larger population, it's hard to be sure that the subjects selected are truly representative of the larger population. Think back to our discussion on sampling. Random selection means that each subject has equal opportunity to be selected, but this isn't always the case. The probability or chance that a random sample will differ from the population mean is called sampling error. We can calculate this error by looking at the difference between the sample mean, or x bar, so that's the x with the bar over it, and the population mean, which is that, you see it on the screen there, it looks like a little u, mu, we would call it. Because a sampling distribution represents a normal curve, we can determine the variability of the sample from the mean. We do this by determining the standard error of the mean. The standard error of the mean equals the standard deviation of the sample divided by the square root of the sample size. So the square root with the n, that refers to the square root of the sample size. The standard error shows how close the sample mean is to the population mean. This can help us or help give us a better picture of the data and the distribution curve. Another statistical term that is often used is confidence intervals. A confidence interval represents the range in which it is believed the statistic falls. A confidence interval takes into consideration the sample statistics and the accuracy of the statistics, so the sample error of the mean. The formula for a confidence interval is, it's on your screen there, but it is x bar, or mean of the scores, plus or minus the probability percentage, the z-score, times the standard deviation of the mean. Whew. The probability percentage refers to the standardized z-scores. You can do calculations for these, and they're also provided. So you can look these up in tables. So for example, on page 802 of your book, Appendix A, Table A1, this is a standardized z-score table. So take a second to look at the appendix and look in the column marked Z, which means the standardized mean of the population. This table represents a one-sided or right-sided tail. So instead of getting 0.05, you would look for 0.025. You'll find this on page 803, second grouping in the far right column. The z-score is 1.96, and for a two-sided tailed curve would represent a plus or minus 1.96. So a confidence interval of 95%, the z-score equals plus or minus 1.96. When estimating the confidence interval, this z-score would be put into the formula. All right, so you're still with me? So let's do an activity. So let's calculate the 95th percent interval, or 95th percent confidence interval for the following. We have an x-bar of 40, standard deviation of 8.8, and a sample size of 42. So quick hint is you need to calculate the standard deviation of the mean, and to do this, use this formula that's on the screen here. So based on the formula that's on the preceding pages, calculate the 95th percent confidence interval based on this information. All right, I'm going to walk you through the steps. I know it's a lot, and this isn't a statistics course, but here we go. So step one, calculate the standard deviation of x bar. And if we plugged in the information that we have 8.8 and we have 42, we get a number of 1.36. Then we're going to find the z-score for the 95th percent confidence interval. We already know that's 1.96. So now let's plug this information into our formula. We know that our x bar is 40, so our formula would be 40 plus or minus 1.96 times our standard deviation of that mean. So our confidence interval is 40 plus or minus 2.67. So our confidence interval is 37.33 and 42.67. How did I get those? I subtracted 2.67 from 40 and I added 2.67 to 40. So our answer is we are confident that 95% of the population mean falls between 37.33 and 42.67. What happens when we have small samples? Are z-scores appropriate? Well, z-scores actually are representative of large population-based samples. When we have small sample size, typically samples below 30, we would use a t-score. And t-scores represent flatter, wider curves. The formula we use for t-score is similar to what we used for the z-score previously, so how we calculated that previously. However, when selecting the proper score from the table, we would use something called degrees of freedom. And so degrees of freedom is a formula. We take the sample size and we subtract 1. So the n represents a sample size and we subtract 1. And then we would look this data up in the data table. So here's an example of a t-score distribution table. At the 95th percent confidence interval with a degrees freedom of 9. So here I'm saying if our sample size was 10, our degrees freedom would be 9. We would follow down the table, and where they intersected would be at 2.262. This represents the t-distribution for degrees freedom of 9 and a confidence interval of 95%. Okay, next activity. Calculate the 95% confidence interval using the following information. We have an n of 18, x bar mean of 5, and a standard deviation of the mean of 2.0. What do we get? All right, let's do the math. So we need to calculate the degrees freedom. So we were given that we had a sample size of 18. So 18 minus 1 is 17. That's our degrees freedom. We're looking up at the t-score, right? Not the z-score, because we're below 30 for our sample size. We see that, I'll give you the number. If we looked it up, our confidence interval with the degrees freedom of 17 would be 2.110. And now let's do the math. We plug in our information. We know that our mean is 5.0 plus or minus 2.110, which is our t-score, times the standard deviation of the mean, which we were given. So if we did everything out correctly, we get our the confidence interval is 0.78 and 9.22. How did I get that? I subtracted 5.0 from 4.22, and I added it to 4.22. This means we are 95% confident that the population mean falls between 0.78 and 9.22. As the sample size increases or the interval gets narrower, we can be more precise in predicting our confidence interval. So this is a pretty wide confidence interval. So here's another activity. So try it again and see what you come up with. And here are your answers that you can check against. All right, this is where we're going to end our presentation, round one, part one on statistics. So take a break. This can be really overwhelming, I know. Be sure you're reading the chapters, complete any assignments and activities due this week. If you have questions about anything, don't hesitate to contact me. Reach out as soon as possible, and I'll get back to you. Thanks, and have a great brain break.